Good evening, everyone. My name is Anesti Milsina, and in this presentation, I will be discussing my specialized project titled Lung Cancer Detection Using AI, a deep learning approach to early diagnosis. The aim of this project is to develop an artificial intelligence system capable of detecting lung cancer from CT scan images using deep learning techniques. Throughout this presentation, I will explain the problem being addressed, the methodology, the proposed AI models, expected results, ethical consideration, and finally demonstrate the project implementation. Lung cancer remains one of the deadliest diseases worldwide. According to the World Health Organization (WHO), it is responsible for approximately 18% of all cancer-related deaths. The major issue is not that treatment is ineffective. Instead, the biggest challenge is late diagnosis. Research shows that patients diagnosed as stage 1 have a 5-year survival rate of around 56%, whereas patients diagnosed at a later stages have a survival rate of only about 5%. Although hospitals use low-dose CT scan, many long noodles are still missed because radiologists often have very heavy workloads and interpretation can vary between specialists. This motivated my project. The objective is to build an AI assistant screening system that automatically analyzes CT scan and highlights suspicious lung nodules. Rather than replacing radiologists, the AI acts as a decision support tool that improves consistency and help identify cases that may otherwise be overlooked. Methodology. The project follow a structured methodology consisting of several important components. First are the software tool. The development of environment includes Jupyter Notebook for model development, VS Code for programming, and GitHub for version control and project management. Next is the dataset. Two internationally recognized medical imaging datasets are used, LIDC-IDRI and Luna 16. These datasets contains thousands of annotated lung CT scans that are publicly available for academic research and have been anonymized to protect patient privacy. The project framework follows the CRIPS-DM methodology, which stands for Cross-Industry Standard Process for Data Mining. One advantage of this framework is that it is iterative. The model performance is unsatisfactory. The project can return to earlier stages and improve the dataset or pre-processing before retiring. The programming language using Python is because of its extensive AI ecosystem. The major libraries includes TensorFlow, Keras, OpenCV, NumPy, Pandas. Each library performs a different role from image pre-processing to neural network training and data analysis. The main algorithm investigated are ResNet 50, 3D-UNet, VNet, and GuardCam. GuardCam is particularly useful because it provides explanatory by showing which regions of CT scan influence the AI precipitation. Next one is model architecture. This project compares two different deep learning approaches. The first is ResNet 50, which is a two-dimensional convolutional network neural network. Its advantage includes transfer learning from ImageNet, faster training, lower GPU requirements, strong performance on individual CT slices. However, it is only analyzes one image slide at a one time and therefore loses information between slices. The second approach uses 3D-UNet and VNet architectures. These models analyzes the complete CT volume instead of individual slices. This their advantage includes better preservation of spatial information, improved understanding of tumor shape, higher performance in medical imaging tasks. The disadvantage is that they require significantly more computational resource and longer training time. The project target is to achieve an area under the curve or AUC of at least 0.90 on the RIS dataset. The project defined several performance metrics on results and expected outcomes. The primary metric is AUC with a target of greater than 0.90, which I have already mentioned before. Sensitivity is also very important because mining a cancer could have serious consequences. significantly measures how effectively the system avoids false alarms. Another metric is the F1 scores, which balances precision and recalls. The expected output includes a trained deep learning models, GAD-CAMS visualization, performance comparison with public research, a complete project report. To ensure reliability, the model is validated using k-fold cross-validation, allowing every sample in the dataset to be evaluated. Now, I will be briefly demonstrating the project implementation. So look carefully. I will be closing my face cam. Okay, well, I finally demonstrate all of the samples. So, another topic is social, ethical, professional, and legal consideration. AI intelligence has the potential to improve healthcare by providing faster and more consistent diagnosis, especially in the areas where radiologists are limited. However, these are also important ethical consideration. If the training data is not sufficiently diverse, the model could become biased and perform less accurately for certain pa- patient group. To minimize this risk, the demographic distribution of the dataset should be carefully evaluated. From a professional perspective, development follows the BCS code of conduct, ensuring responsibility, integrity, and patient safety. Legally, both of the LIDC, IDRI, and Luna 16 datasets are fully anonymized and comply with GDPR principle. If deployed in hospital, the software would also require appropriate medical device certification before the clinical use. Conclusion. To conclude, lung cancer remains one of the leading cause of cancer related deaths, largely because diagnosis often occurs too late. This project demonstrates how deep learning techniques can assist clinically by detecting lung nodules more accurately and consistently. The project combines publicly available medical dataset, the CRIPS-TM framework, model convolution, natural networks, and explainable AI techniques such as GrandCam. The overall goal is to achieve high diagnostic performance while maintaining the transparency and supporting clinical decision making. Although AI cannot replace experienced radiologists, it can become a valuable tool that improve early detection and ultimately contribute the better patient outcomes. Thank you very much for watching my presentation. I am happy to answer any question. Thank you.